Let us start lecture 45, and the course is on phase diagrams in single component and binary systems. And today's topic that will be the discussion on non-ideal solution, and today we will look at a regular solution model, and we try to find out an expression for del Hmix. Okay. Now, from the last class, if you recall, we have seen that for non-ideal solution, we can express concentration in terms of activity, and except in case of ideal solution, where activity of a component in a solution is equal to the mole fraction of the same component in the solution. That means the activity coefficient, which is gamma of that component, is 1, but when we talk about non-ideal case, that activity coefficient, which is gamma of that component, can be greater than 1 or less than 1. If it goes to greater than 1, we have positive deviation from ideality. If it is less than 1, it goes to negative deviation from ideality. And we have also seen this positive as well as negative deviation does not mean that the value becomes negative. Rather, we deviate that straight line variation of activity with mole fraction. That line, from that line we deviate, either we go downwards or we go upward. Okay. So, now we, for non-ideal case, non-ideal solution, we have seen that of course, here one condition needs to be considered, that is pressure constant and composition constant. Okay. And I is the component we are talking about. Now, accordingly, we have seen that gamma is basically, which is activity coefficient, and it comes from A I equal to gamma I x I. Okay. So, this gamma could be having greater than 1, gamma could be having a value of 1, gamma could be less than 1. This is positive deviation from ideality. This is ideal solution, and ideal solution means Raoultian behavior. Okay. And this is negative deviation from ideality. And we have also seen that gamma, when it is greater than 1, del H mix 0, or it is endothermic. Means the solution formation is endothermic, the solution system will accept heat from surrounding. And second time what we have seen, gamma is less than 1, del H mix is less than 0, and that is exothermic, and both the cases are actually dependent on bond energy of AA, bond energy of BB bond, and bond energy of AB bond in case of binary solution of A and B. So, that is what we have learnt, and this relation we could set up because we have seen that at a very dilute concentration or dilute solution, okay, if we talk about B in A, that is a solution, that means x b tends to 0, that time we have seen that A b equal to gamma b x b, and this that time this one is a constant. Okay. Otherwise, that gamma b can be a variable, okay, over the entire composition range. So, this particular, and this is a straight line which is Henry's law, and it has a relation with P b equal to K b x b, where this is also Henry's law, this is the partial pressure of B in contact with the solution system A b. Okay. And from there, and remember this one was actually explained on the basis of the relation of bond energies, whether A b bond is highly negative as compared to A A or B B type, or A A or B B, the similar type of bonds can be highly negative as compared to A B. So, that means this particular positive greater than 0 or less than 0 del H mix, that time that must have a relation with these bond energies. Okay. Now, we have to get into that bond energy part in order to derive the expression for del H mix. And of course, if you talk about ideal case gamma equal to 1, that time del H mix equal to 0. Okay. So, there will be no heat effect. Okay. And that is also related to this, because that time it will follow Raoult's law. So, that time that will follow Raoult's law. Okay. Now, and Raoult's law is basically P b equal to constant B and P b naught. Okay. So, that is the kind of Raoult's law we have talked about. Fine. Now, we could see that since this del H mix, if it is positive or negative, that has a strong relation with the bond energies of A A type, B B type and A B type, our entire effort will be now finding out the relation between these three whenever we do experience such kind of values for del H mix. And in order to do that, we will use a model called regular solution model. And this is also called quasi-chemical model. Fine. So, this model allows me to find an expression of del H mix as a function of E A A, E B B, that is those are the bond energy, A B, then we have mole fraction X A, X B of A and B in the solution, and we can also have a relation with their coordination number. Fine. In fact, this coordination number would allow us to find out the number of bonds of A A type, B B type and A B type. And our entire discussion will be on for making binary solution of A and B metals. Okay. So, that will be our discussion point. Now, while coming to the finding of expression of del H mix, we have to understand the kind of assumptions we take in order to set up the regular solution model. What are those assumptions? These are very important assumptions. On the basis the regular solution model and expression for del H mix will be found out. Okay. Now, first assumption is basically we consider that chemical effect is considered for and we have to ignore couple of things like strain energy effect, valency effect. All those effects can actually influence the degree of solution formation. So, we will not consider them. For example, strain energy effect. Let us say A and B are combined, these are the two metals and they have different size, atomic size. So, once and for example, one is very small, another one is very big. So, then there would be a definite situation of strain energy, okay, or sometimes you have a substitutional solid solution. Okay. So, that time you have A and B atoms are placed at the lattice points of that particular crystal, and in that lattice points one of the for example, initially you start with A lattice points, that means A crystal, and now you keep adding B and the B atom is much bigger than the A atom. So, definitely that B atom will try to push those A atoms while sitting at the A lattice points, one of those A lattice points. So, that will give a kind of strain to that matrix, and whenever the system feels that strain, definitely the solubility will be compromised. Okay. So, that is what these other things are not considered, only chemical effect is considered. Now, second is we consider bond energy, bond formation and bond energy. Okay. So, of AA type, BB type and AB type, but there is a condition. So, that bond formation is only possible with nearest neighbor atoms. Okay. So, what do we mean by nearest neighbor? Let us consider a BCC unit cell. Okay. So, now we have a BCC unit cell, let us say this is BCC unit cell. It means that body centered cubic, where you have one lattice point at the center, body center, and other lattice points are at the all the corner points. This is the body center and all corner points. So, this is a BCC unit cell, and where the atoms are actually at the body corners and one is in the body center. So, now if you try to look at, and this is a perfect cube. So, that means all the sides if of length A are equal. Okay. Now, if I try to find out, we try to look at this body centered atom and try to see what are the closest positions of those atoms, we will see that all those corner atoms will be situated at the same distance from the body centered atom, and hence we can have bond like that. So, we can have a bond, one bond like this, the another bond is like this is another bond, this is another bond, this is one, this is another, this is another, and this is another. So, that means we could see that, and all those distance, if you try to look at, let us say this is, let us say this length is, let us say A, and then definitely this length is, let us say R. So, this length would be also R, like that all those lengths connecting to the body centered atom with the corner atoms are all same distance. So, that means those are the nearest neighbors. Now, if I try to look at another body center Let us say let me draw another body center. So, let us say this side there will be another body centered atom. Sorry, there is a body centered cell. Okay. And here there will be another body centered atom side by cell. We will not have, and then if we connect these two body center, this is the connection point, connection line between the body center of one cell to another, and that time this particular body center atom, two body center atoms will not have any interaction. So, that we actually ignore that interaction. So, only the interaction that is possible with the nearest neighbor. So, this bond formation is only possible with the nearest neighbor, and that is what we have to consider the coordination number, which is considered as Z of a crystal. Okay. So, that will tell us how many bonds can be possible. Okay. We can calculate that. And this bond energy all will be, and these bond energies are EAA, EBB and EAB, all those bond energies are negative in nature. Why? That bond is formed if you have an atom, let us say, and another atom is positioned itself at an infinite distance. When they are brought closer to each other, so there will be a lot of attractions. But once they come very close to each other, the outer cell electron will have a repulsive force coming up. Okay. So, that attractive and repulsive force will balance each other at a particular location, and that particular distance between two atoms, that is called the bond length, and the energy, the potential energy minima, that is the potential energy minima there it will exist, and that minima point with reference to the 0 value will be the bond energy. Okay. So, if I try to look at the bond energy, so this is distance, let us say r, and this is positive force and this is negative force, you will have an potential energy. If we plot, we will get a plot like this. Fine. So, this distance, and this is 0 value, this distance corresponding to bond energy. Fine. Let us say we are considering two atoms, this is one atom, this is another atom, and this two atom will have, let us say, AA type. So, that two atom will actually have EAA bond, and every time there will be the negative value. So, all the bonds have different negative values. Okay. Now, the third consideration what we have to consider. Okay. So, the third consideration, it says that del V mix, that means once those two pure metals are mixed together to form a solution. So, that solution would have some volume, and before that the solution can have a different volume, but these two volumes, if you combine them together, then the volume change. So, this is the volume change due to mixing or solution formation is considered to be 0. So, there will be no volume dilation, okay? No volume change due to solution formation. Okay? So, that is another assumption we are considering. Okay? Then fourth is we will consider that AA, A, B and AB, the solution, would always have the same crystal structure. So, that means we consider the Z to be same before mixing and after mixing. Okay? So, that is another assumption we can take. So, these are some of the major assumptions on the basis of which we will actually develop our model. Okay? So, now let us look at the actual model part. Now, we are taking A and B, these are the two metals, and we have taken the number of, let us say, number of atoms. These are the number of atoms that are taken, and the temperature and pressure both are fixed, and when you add them together should yield me a value called N0. Let us say that is Avogadro number. Okay. It means that 1 mole solution formation. Okay. So, both of them have the same crystal structure. And if I try to look at the mole fraction, so Xa can be written as Na divided by N0, and Xb, which is the mole fraction of B, equal to Nb divided by N0. Okay. So, we can see that Xa plus Xb equal to 1. Fine. In fact, we have missed one more assumptions. Let me just write down that assumption. We will have consideration of entropy and of mixing. So, that entropy of mixing can be expressed as R Xa ln Xa plus Xb ln Xb, and this is coming mainly due to configurational entropy. All other entropy part entropy are ignored. So, this is also one more assumption, and that we can see because we have defined now what is Xa and Xb. So, this term would come up. Where it would come up? We have seen that delta G mix equal to del H mix minus T del S mix. So, here this term is coming up, and that value will be decided by this configuration entropy of both A and B, okay, when we mix them. All other entropy means, let us say we can have vibrational entropy like that. So, those are all ignored, only configuration entropy is considered. So, now we can say that, so this is once we have this, then we can also find out what is G2. G2 is for solution equal to G1, which is unmixed plus delta G mix, okay. And final interest would be to find out this, but before that, in case of ideal case, this equation was very simple. So, del G mix is nothing but minus T del S mix, since del H mix equal to 0, fine. But when we talk about non-ideal, so that time we have to consider del H mix into the expression, fine. And then the pattern of that particular free energy plot for del G mix as well as G2 solution will be changed, okay. So, this will be non-zero value. We will find later see whether it becomes positive or negative, how it changes. So, these are the conditions, and on that basis we will now move ahead, and this 1 means 1 mole and Avogadro number, and now also it coming out to be 1 mole solution both ways. Now, let us look at del H mix expression. We will find out. Now, when we talk about AB solution formation, so we can have 3 bonds. What are those 3 bonds? AA, BB and AB, and they have the energies EAA, they have energies EBB and energies EAB, bond energy. Now, if we try to get the number, so that bond number, that can be expressed as PAA, PBB and PAB. These are the numbers, and that numbers can be calculated using this one, and same crystal structure, that is we have to talk about coordination number, which is Z. So, this Z is basically what are the nearest neighbor atoms around another atom. Okay. In case of BCC, this coordination number is body centered cubic, it is Z equal to 8. For FCC face centered cubic, Z is equal to 12. Like that way, we can find out what will be the coordination number, and accordingly we can find out what are the number of bonds. Now, once we have, let us say, a solution is formed, so then we can find out after formation of solution, we can have all 3 bonds, all 3 bond energies. We can find out what is the energy of solution. So, energy of solution is, it is basically all the energies coming up from all the bonds of AA, BB and AB type. So, we can say PAA into EAA plus PBB into EBB plus PAB EAB. So, this is basically after the formation of solution. But before that, so then Hmix. Now, unmixed, and this is before solution formation. Unmixed would be, that time we will only have AA type bond. So, for A case, and then B type bond, BB type bond for B case, pure B case. Okay. Now, let us find out what would be the PAA and PBB. And remember, these numbers would be different. This number and this number, they are not same, because in this case, some of those lattice points of A type, let us say I am mixing B into A. So, that means some of the A sites are replaced by B type. So, that means the number of bonds of AA type would change, and there would be existence of BB type bonds also, as well as AB type bonds also. So, these two case, this one and this one, they are not same. Okay. Now, let us find out the bond numbers. Okay. Now, let us say I have taken A atom is like open circle and B atom is like closed circle, and they are the bonds. Now, when we try to form by combining these 4 atoms, 2 AA and 2 BB, then we can get 2 AB type bonds. So, it means that 1 AA type and 1 BB type bonds is equivalent to 2 AB type bonds. Now, another part, let us say I have a crystal situation like this, 1 A atom let us say if I talk about A atom, let us say this is a kind of atomic arrangement, all A type atom. So, we can have nearest neighbor like this, these are the bonds, and let us say this is A type, pure A, and here Z is equal to 4, fine. This is a hypothetical situation, let us say 4. So, now we can actually, these are all A type. Now, when we talk about A type bond, considering that all are A and each A atom, how many bonds it will have with all the other A atoms surrounding it. So, now this is one A atom, this is another A atom. Now, when we join them together, if we consider this A, then this A is forming one bond and this A is also forming another bond. So, that means, but it's finally is leading to one bond. So, that means, when we talk about two AA atoms and forming a bond, each atom is considered twice for the bond formation, but actually we have one unique bond of AA type. So, that means, if we see that or each A atom, one A atom is considered twice. So, now if I try to find out in this case what is the number of bonds, now since it is Z and we have if I consider this is the lattice. So, that means all the corner atom will have 1/4 of contribution to that particular cell and one is at the center. So, that is another full atom. So, we can see that there are two A atoms in that unit cell. So, when we talk about that, so 2 atom into Z, so these are basically the total and these. So, so each atom is considered twice. So, we can say that these are the number of pairs of these are the number of this divided by, we can say this is the number divided 2 should be the number of AA bond. Okay. So, we can see that Z is 4. So, we can see that this is coming out to be 4, fine. Now, if I try to look at any number of A atom in pure A and Z is basically the coordination number, so then total A bonds would be equal to Na Z by 2. We can also say the number of pairs of sites. Okay. So, here all the sites are occupied by A atom. So, this is the number of A bond. So, we can say PAA equal to NaZ by 2. It means that NaZ equal to 2 PAA. Now, if I try to look at this is NB, this is one case. The second case is NB number of B atom, and when we talk about pure B, and here also Z is the coordination number because crystal structure does not change. So, then PBB should be equal to NBZ divided by 2. It also gives me NBZ equal to 2 PB. Okay. So, that means, if I try to consider the pure case, each A atom, let us say I take a reference of one A atom. So, how many A bonds it will form, that will be decided by the number of A atom into the coordination number divided by 2, because each A atom is considered twice. So, that is what the division, that 2 is coming, that is divided, that with the 2 it is divided. Okay. So, accordingly we get these two cases for pure case. Now, we have to talk about solution, a mixture. So, that means in the mixture of A and B, if I talk about B is mixed, so this is the case, let us say. Okay. Now, the total number, so that means if I talk about A atom reference, A atom is to be considered for bond calculation. So, that means number of A atoms into the number of bonds per A atom definitely. Okay. If I try to find out this number, so it can have AA bond as well as AB bond. Now, when we talk about A atom making bonds with A, so each A atom is considered twice. So, that means the number of bonds will be definitely as per our condition, as per our previous discussion, it has to be 2 PAA, that is the number of AA type bond. Now, when we talk about AB, each A will have, it has to be, will have to be considered once to form AB bond, because we are talking about bond formation with reference to A only. So, that case, if we talk about number of AB bond, which is AB. So, this should be then equal to PAB plus 2 AA, which should be equal to Na into number of bonds per A atom, which is Z, because Z is the coordination number. Okay. So, this is nothing but Z. So, this is one equation we are getting. Then from there we can get PAA equal to NAZ minus PAB divided by 2. We get this. Now, the second one, we are talking about B is mixed with A. Now, same condition, if we take B atom as the reference, is as considered, B atom is considered for bond formation. So, that will be same as number of B atoms into number of bonds per B atom. So, this is nothing but Z and this is nothing but NB. So, equal to NBZ equal to, now we have to consider AB type bond. So, when we talk about AB, if I take B as the is considered, so the B will always have to be considered once to form AB type bond. So, then we have one contribution, and then when we talk about BB type bond, then we have to consider PBB. Okay. So, then it gives me PBB, we can write PBB in terms of PAB, NBZ minus PAB divided by 2. This is another. Now, when we write Hmix should be equal to PAA EAA plus PBB EBB plus PAB EAB Now, I replace, this is where everything what you have done is basically with reference to mixing conditions, because here now we are considering mixture, fine. Now, when we talk about that, we have to talk about this Hmix, which is nothing but, now I am replacing PAA type, which is NaZ minus PAB by 2 EAA plus NBZ minus PAB by 2 into EBB plus PAB EAB. So, then it becomes, if I simplify it, if I break all the terms, then we should get like this: NaZ EAA by 2 plus NBZ EBB by 2. This is one part. The second part is PAB EAB minus EAA plus EBB by 2. This equation we are getting. Now, if I find out, if I try to find out what will be the, this is basically before mixing. So, then E unmixed is nothing but PAA EAA plus PBB EBB should be equal to NaZ EAA by 2 plus NBZ by 2 EBB, fine. So, this is E unmixed. We have got E unmixed as well as E mix. So, then for the solution formation at a particular temperature and pressure, the energy change for mix should be equal to E mix minus E unmix. So, then it would be equal to, now if I try to look at this part is nothing but E unmixed. So, then E unmixed plus PAB EAB minus fine minus E unmix. So, these two will cancel. So, del E mix equal to PAB EAB minus EAA plus EBB by 2. Now, we see that entire whatever we have done till now, all those formulations, finally, we are finding what is the energy change, and this is, remember, this is basically the energy change due to solution formation at a constant temperature pressure, that is decided by the number of AB bond and the energy difference between EAB with the total energy of EAA and EBB divided by 2. So, this term we can consider to be the energy difference between AB bond energy and half of similar type bond energies. So, which is EAA plus EBB by 2, and this is EAB. Okay. So, now let us stop our discussion now. So, we have found this expression. So, then the next class we will try to explain this particular expression, and in fact, this particular energy difference term, this term will be explained and with reference to the solution formation, and we can actually qualitatively discuss that whether we can get a terminal solid solution or compound or cluster or let us say phase separation. Okay. Those kind of thing we can discuss or short range order, fine. All those things can be discussed with the help of this particular energy difference. So, till then let me stop here. We will continue our discussion for the expression of for finding expression for del H mix, and this is half of it. The next half will be discussed in the next class. Thank you very much.